Hello networking enthusiasts. Welcome to our deep dive into building a fully routed Kubernetes cluster with Calico CNI, one of the most popular container network interfaces for Kubernetes. In this series, we'll explore the intricate workings of traffic flow, delve into the utilizing of BGP, and harness the power of ECMP for efficient load distribution. In part 1, I guide you through constructing the cluster and pairing it with an external router to expose Kubernetes workloads seamlessly. Part 2 will elevate our setup by introducing load balancing and configuring external traffic policy in local mode. I'm Philip, your guide on this journey. Let's get started. Let's start with some theory to understand how the networking piece of the solution works. There are two Kubernetes nodes, Kube1 with 192.160.80.58 IP, being both the master and the worker node, and Kube2 with 192.168.80.59 IP, that's just the worker node. The pod subnet is 10.244/16 and the service subnet is 10.96/16. In CNIs like FLANNEL that uses an overlay network, we would see a layer 2 bridge, usually named CNI0, and bunch of virtual Ethernet pairs that connect ETH0 interface within the pod to VTH interfaces within the CNI0 bridge on the host. When pods within the same node want to talk to each other, the traffic goes via layer 2 bridge. The first difference with Calico fully routed mode is the lack of the layer 2 bridge. Each pod is connected using a VTH pair directly to the host. Basically, pod's networking namespace is directly connected to host networking namespace with the virtual Ethernet pair. Every time a new pod is created, its IP is added to the host routing table with information that is reachable via the Kali VETH interface. So, if two pods on the same node want to talk to each other, the traffic first goes to the host and then is routed to the pod. Thanks to this approach, we avoid the unnecessary complexity and performance overhead of additional layer 2 bridges. Moreover, because there is no encapsulation involved, the packet size stays the same. It fits within the standard 1500 byte MTU. Let's run a quick speed test between the two pods running on the same node. On the left we have FLANNEL CNI and on the right we have Calico CNI running in the routed mode. The results are comparable. Additional layer 2 bridge did not slow down the transfer rate. Getting back to our FLANNEL setup. What if the pod wants to talk to a pod on a different node? Here's where a special virtual network interface called FLANNEL comes into play. Traffic to pod on a different node is sent to FLANNEL interface, where it is encapsulated into VXLAN, sent via ETH0 interface to the other node, where it is forwarded to FLANNEL interface, where the traffic is decapsulated, sent to the bridge, and then through VETH down to the pod. VXLAN is a technology where full layer 2 packets are put inside an UDP envelope. The VXLAN header is 50 bytes. That leaves us with 1450 bytes for the data. Let's analyze the same scenario but with Calico in fully routed mode as the CNI. When a pod wants to talk to another pod located on a different node, first the traffic will go to the host, that's the first hop. Here it will find the route pointing to the other node, then the packet will be forwarded accordingly. The other node will check its routing table and direct the traffic to the target pod via the VETH pair. Plain and simple. No bridges, no overlays, no NAT, just routing. Let's run the same speed test, but this time between pods running on different nodes. On the left we have FLANNEL CNI and on the right we have Calico CNI in fully routed mode. This time the transfer rate difference is significant. Overlay mode is 2 times slower than fully routed mode. Before we dive deeper into the ins and outs of how it's wired, let's first build the cluster. I'm on Kube1 and have all my prerequisites, that is, container runtime and Kubernetes binaries installed. There's a detailed video that describes the installation process if you are interested. Let's list the settings that will be used to bootstrap the cluster. Here's the pod subnet, service subnet, API and kubelet IPs. Let's run the installer. Now let's copy the kubeconfig file that holds information about Kubernetes cluster to our home directory. We'll then use this file to connect to the cluster. To have it out of the way, I will go to the other node, that's kube2, and modify its configuration file so it can join the cluster. I will paste the join token here and paste the CA cert hash here. Then let's issue the join command. If we look at the nodes, they are both not ready. That's to be expected. Kubernetes itself does not include built-in networking solution and relies on container network interface plugins to provide the networking capabilities required for communication between pods and services within the cluster. Let's remove the noSchedule taint so that we can schedule pods on kube 1, that's the master node. Now it's time to install our Calico CNI. There are a few ways to do it. We'll use the recommended one, that is by deploying an operator which manages the installation, upgrade, and general lifecycle of the Calico cluster. Then we need to provide Calico installation configuration. I will download the template and make a few modifications prior to applying the installation configuration resource. Let's update the pod network range to match our configuration. That's 10.244.0.0/16. Because our nodes are simple on-prem VMs with direct reachability, we don't need any encapsulation. So I will set the encapsulation to none. Mind that if you'd like to avoid dependencies on the underlying network or on a specific cloud provider, you can configure Calico to run in cross-subnet overlay mode. If you're interested in how to do that and how that works, let me know down in the comments. Calico supports both VXLAN as well as IP-IP tunneling. There's also one important parameter that we need to be aware of. That's the block size. It specifies the size of CIDR block that Calico assigns to each node. In our example, /26 is 64 addresses. What will happen is Calico will carve out /26 out of the pod CIDR and assign it to a node. So each node gets a /26 chunk of IPs, and pods on that node are assigned IP addresses from this chunk. If a node runs out of IP addresses for its pods, it will be assigned a new /26. Whether to use a smaller chunk or a larger chunk is up to you. Smaller block size may lead to more frequent allocations and slightly higher overhead. With larger block size, you'll have more efficient IP address allocation for nodes running many pods, but it may lead to underutilization of IP addresses if nodes have fewer pods than the block can accommodate. Let's apply the configuration. There's a dedicated CRD called Tigera Status that provides detailed status information about Calico components and resources. We need to wait for all components to become available. Okay, our initial configuration is ready. Last thing we need to do is install Calico CTL tool. This is a specialized tool for managing Calico's advanced networking and security features. It provides capabilities beyond what kubectl offers, enabling detailed configuration, monitoring, and troubleshooting of Calico resources. Let's download it, then allow execution, and move it to USR local bin. First thing first, let's see how our pods talk to each other within the same node. From a high-level perspective, every time a pod is created or destroyed, Kubernetes will call the Container Network Interface API. The CNI Network plugin handles creating and connecting the pod's network interface. However, there's yet another plugin called the CNI IP Address Management plugin, EPAM for short, that takes care of assigning and managing the pod's IP addresses. Let's see the assigned IPs and overall IP usage with Calico CTL EPAM show command. There's the whole /16 pod subnet. 7 IPs are used and over 65,000 are free. Down below, we see individual /26 blocks allocated to each node. Following one-liner can tell us exactly which block is assigned to which node. I will create a deployment with 2 Alpine Linux pods. Here's the manifest file. Only thing to mention is that both pods will be spawned on kube 1 node. Let's also create a single pod on Cube2 node. This time the node name is set to Cube2. Okay, both deployments are ready. First deployment has two pods running on the same node. Second deployment has only a single pod. Let me go to the first pod on Cube1 node and enter its shell. Let's also enter the shell of the second pod on the same node. I will list the IP address of pods. Mind that MTU is 1500 bytes, unlike 1450 for VXLAN or 1480 for IP-IP encapsulation. Let's trace the route between the pods running on the same node. First hop is the Cube1 node, second hop is the target pod. Mind that if we look at the routing table of Cube1, we'll see that both pods' IPs have direct routes. Let's see how the traffic flows between pods on different nodes. I will switch to the shell of the pod on Cube2 node. Let's check its IP address. And now trace the route from pod on Cube1 to pod on Cube2 node. First, the traffic goes from pod to Cube1 node via the VETH pair. Then the traffic is routed to Cube2, and from there it goes to the target pod via another VETH pair. The question is, how does the Cube1 node knows where to route the traffic to? If we consult the routing table on Cube1, asking for the route to pod on Cube2, we'll discover that Cube1 node is aware of the /26 network sitting behind Cube2. Turns out that each Calico node is running a BERT BGP software. If we look at our Cube1 node, we'll see a BGP session with Cube2 established. This session is then used to exchange routes. Let's switch to daemon sets, go to Calico node, and enter the shell of Calico node pod on Cube1. We can then enter command line interface to interact with BERT routing daemon with BERTCL command. There's the BGP session with Cube2. We also have a static route covering our /26 that's assigned to our Cube1 node. This route is then advertised via BGP to Cube2 node. If we go to Cube2, we'll see that it has this network in its routing table learned from BGP. Also, the other way around. If I go to Cube1, I can see what routes we learned from Cube2. In fully routed clusters, accessing Kubernetes workloads from outside the cluster works a bit differently. Since the cluster uses BGP for internal route exchange, we can set up BGP peering with our on-prem routers to access the workloads. In other words, we learn the routes that Kubernetes cluster is advertising, allowing the rest of the network to access the applications hosted on the cluster. I have a single VM running BERT routing software on the same network as Kubernetes nodes. We'll set up BGP peering with both Cube1 and Cube2. Important thing to mention is that our router is running under a different autonomous system than the Kubernetes cluster. Router has AES number 64513 and both Kubernetes nodes have AES number 64512. Let's quickly set up our peering and see what happens. BERT keeps its own routing table. We can import routes to that table from BGP or other protocols. We can also export routes from that table to other protocols. However, this table is not used for making routing decisions. For the kernel to use those routes, we need to export them from BERT routing table and import them into kernel routing table. Here's my BERT configuration. Here we interact with the kernel routing table. Import none means we don't want to learn any routes from the kernel. Export all, we want to inject all routes that we have in our BERT routing table to the kernel routing table. In other words, whatever we learn from BGP is put in the kernel routing table. Here we define BGP peers. Those are the servers we'll be exchanging routes with. We'll peer with Cube1 and Cube2. Peering setup will be identical for both servers. Our own AES number is 64513 and the Kubernetes cluster AES number is 64512. We want to learn all routes advertised by the Kubernetes cluster and import them into the BERT routing table. We don't want to advertise any routes to the cluster. Our router will peer with both Kubernetes nodes, learn all routes they advertise and inject them into the router's kernel routing table. For the BGP peering to work, we also need to perform the setup on Cube1 and Cube2. Let's go to Cube 1. First thing we need to do is set up the BGP configuration resource. I have one already defined. If we look at its definition, we'll see Kubernetes AS number, service CIDR range that we want to advertise. By default, only the pod network is advertised. If we want to advertise service IP range, service external IP ranges, or load balancer ranges, we need to explicitly put them in the configuration. Let's apply the configuration. Okay, BGP configuration resource is ready. Now let's define our BGP peers. To do that, we'll create a BGP peer resource. Here's the peer name, peer IP, that's the IP of the router, and peer AS number, that's the AS number of the router. Let's apply the configuration. Our BGP peer resource is there. Cube 1 already had BGP session set up with Cube 2. Now it also has a session with the router. If we look at Cube 2 node, it also has a BGP session with the router. As the BGP peer resource that we created does not have a node selector, it applies to all cluster nodes. So both Cube 1 and Cube 2 establish their own BGP sessions with the router. If we go to the router, we'll see that it has two BGP sessions established, one with Cube 1 and the other with Cube 2. Let's look at BERT routing table. We see some routes learned via BGP, routes that Cube 1 and Cube 2 nodes advertised. Here's the route to pod network on Cube 1, the route to pod network on Cube 2, as well as the route to the service network from which cluster IPs are assigned. First thing I'd like to do is not advertise the pod subnet to the outside world. I don't want servers from outside the cluster to access the pods. I only want to advertise the service subnet. To do that, let's filter out the pod subnet from being advertised by Kubernetes cluster. I will define the BGP filter resource. The action is reject. The subnet that we want to reject is 10.244/16. That's the whole pod network range. Let's create the resource. In order to apply the filter, I will open the peer manifest that defines BGP peering with the router and add the filter. Let's apply the manifest. Moreover, if we look closely, we'll see that BERT is telling us that it can reach the service subnet via .58 IP, that's Cube 1, but also via .59 IP, that's Cube 2. Both nodes are advertising the same subnet, so no matter which node we'll go to, we'll be able to access the cluster IP that's in front of the pods. Let's see some action. I will deploy two WhoAmi pods, one on each node. Those are tiny HTTP server written in Go that provide some operating system and HTTP request information. Moreover, I will create a cluster IP service in front of the pods. Let's apply the manifest file. Okay, both pods are there. One on the Cube 1 node, other on Cube 2 node. A service of type cluster IP was also created. Let's try accessing the service from the router. What can we make of this output? The connection works. We are balanced across two pods, although the router always goes to Cube 1 to reach the service. Let's look at the router's routing table. Indeed, it points to Cube 1 node to reach that subnet. If we look at the BERT's routing table, we see two paths available, but the kernel is using only one. The path exported to the kernel's routing table is the one with an asterisk. It's called the best route. Because the routes have the same cost, we could try exporting both routes, making it an ECMP route. It will distribute traffic across multiple paths that have the same cost. This will help in balancing the load and prevent any single path from being a bottleneck. To do that, let's open the BERT configuration file and add one parameter, merge path on. This will enable multipathing. Let's save the configuration and restart BERT. If we check the kernel routing table, we'll see that service CIDR has a multipath route. The traffic can be balanced across both links. Let's try that. The traffic still goes via Cube 1 despite the ECMP route. The reason for this is by default the kernel will balance the traffic based on the source IP it's coming from. It's called a layer 3 hashing. So the same source destination IP pair will be routed via the same route. To balance the traffic more evenly, let's switch the balancing policy to layer 4. It will also take port numbers into consideration. I will open the kernel configuration file and change the ECMP hash policy to layer 4. 0 is layer 3, 1 is layer 4. Let's save and load the configuration. If I test the connection now, we'll see the traffic routed via both Cube 1 and Cube 2. The load is split evenly across both links. And that wraps our deep dive into building a fully routed Kubernetes cluster with Calico CNI. I hope you found this tutorial insightful and empowering for networking projects. Remember, in part 2, we'll enhance our setup by introducing load balancing and configure external traffic policy in local mode. If you enjoyed this video, please give it a thumbs up and subscribe to the channel for more advanced Kubernetes tutorials. Don't forget to hit that bell icon to get notified when part 2 is released. Feel free to leave any questions or feedback in the comments below. I'd love to hear from you. Thanks for watching and happy networking. See you in the next video.